Wait, I actually put the wrong card. Can you take this back? No, no, no. Because of Stack, you can't pick up that.
Hello everyone, today our group is here to present on the topic stacks. Our group is group number 4 and I am Aditya Kumar. Now let's begin. So let's talk about our outline for the presentation. The first is introduction to stacks. The second is array implementation of stacks. The third is linked list implementation of stacks. And fourth, we are going to talk about application of stacks in nested brackets. And fifth, we are going to talk about application of stacks from infix to postfix. And sixth, we'll discuss about pros and cons of stacks. And at last, we'll talk about real life analogy of stacks. Okay, so what is stacks? A stack is a linear data structure in which insertion and deletion are only allowed at the end, also known as the top of the stack. This is called the top of the stack, or also known as the end of the stack. It follows LIFO, last in first out principle, in which the insertion of a new element and removal of an existing element takes place at the same end represented as the top of the stack. So let's take an example of this pile of books and this pile of coins. So we saw in the earlier video in which my friend wanted to take out one card from the middle of the deck, but according to the principle LIFO, we can't do so. Like for example, in this pile of book, if we want to access it, we can access only the topmost book, or we can either put another book on top of it, or we can only take this book out of the stack. And similarly, we can uh, use this principle in this pile of coins. So both these example have two things in common. That is one, any object can be accessed only from the top. Any object can add it only on the top. So we can consider a stack as an object placed inside a glass jar. So as in glass jar, we can only access the top of it. So say similarly, we can do in the stack. Let's talk about types of stack data structure. The first is fixed size stack. As the name suggests, a fixed size stack has a fixed size and cannot grow or shrink dynamically. If the stack is full and an attempt is made to add an element to it, an overflow error occurs. And if the stack is empty and an attempt is made to remove an element from it, an underflow error occurs. In a dynamic size stack, a dynamic size stack can grow or shrink dynamically. When the stack is full, it automatically increases its size to accommodate the new element, and when the stack is empty, it decreases its size. Stack as an ADT. When we define stack as an ADT, that is a stack data type, then we are only interested in knowing the operation of stack from the user point of view. Means we are not interested in knowing the implementation of details at this moment. We are only interested in knowing what all kinds of operations we can perform on stacks. Thank you.
Everyone, today I, Ritishaa Singh, will be presenting before you all on the topic implementation of stack using array. So in order to implement stack using array, there are following operations: push, pop and peek. Push appends the stack and adds the element to the top of it. Pop removes the topmost element from the stack, and peek checks for the topmost element of the stack and does not remove it. The time complexity for push operation on average is order of 1, because appending an element to the end of this array is a constant time operation, and pop operation also has order of 1 time complexity, because removing an element from the top of the stack doesn't shift other elements. Now, push operation in stack. So before pushing an element into the stack, we need to check if the stack is already full or not. If it is already full, I cannot further add any element into it because it will cause stack overflow. From the given example, the capacity of the stack is 4. The array capacity is 4. I cannot add further any element after index 3, because if I try to add 5 into this array after 4, it will cause stack overflow. Another operation is pop operation. If I want to remove an element from the stack, then I need to apply pop. So before removing or popping element from stack, I need to check if the stack is already empty or not. If it is already empty, it would cause stack underflow. Like in the given example, after removing the element from the 0th index, I cannot further remove anything, because then it would cause the stack underflow. Now here's a code for implementation of stack using a menu-driven program. So in this code, I can see that the first operation given is push operation, that pushes an element into the stack. Another is pop. It returns the topmost element of the stack and removes it. Peek only returns the topmost element and does not remove it. Here's the menu of the program. If the user gives the command 1, then it would push the element. 2, then it would pop. 3, then it would print all the top elements. 4, then it would print all the elements present in the stack. And 5 is given by the user, then the program is quitted. Now if I run this module, and if I push 4 into the stack, and then I check all the elements present in the stack, it is only 4. Again, I want to push 6 into the stack, and then I check all the elements present, then it is 4 and 6. Now, if I want to check the topmost element, then it is only 6. So, it was the implementation of stack using array, and it was the menu driven code for all the operations. Thank you.
How many members you are? We don't know. Not sure. This concept say applies to the stack and we use linked list in that case. If we don't know elements and we can
So my name is Vashita Gupta and my roll number is IPM 05068. Let's dive deeper into what is linked list. So what is a linked list? A linked list is a linear data structure that consists of a series of nodes connected by pointers or references. Each node contains data and a pointer or reference to the next node in the list. Unlike arrays, linked lists allow for efficient insertion or removal of elements from any positions in the list, as the nodes are not stored contiguously in the memory. But the question is, why linked list? We use linked list when the size of the stack is not known, because there is no limitation on the number of nodes that can be created. For example, here, the stack is 34, 21, and 78, that is in a linked list. Here, we can add any number of nodes. But why should we consider the beginning of the linked list as the top of the stack? Let's go for the operations. First operation. Here, a new node will be inserted at the beginning of the linked list. For example, here 50 is inserted in the already stack that is 34, 21, 78, and the new stack becomes 50, 34, 21, 78. Here is the pop operation, where a node will be deleted at the beginning of the linked list. So our stack becomes 34, 21, and 78. The first node that was 50 is deleted. But here we will actually know why we remove or insert with the first node that is the top of the stack. Now let's come to the time complexity to understand this. So time complexity of adding a node at the beginning is big O1, and the time complexity of deleting the first node will also be big O1 because we're dealing with the first node. But now, if we take the end of the linked list as a first node, the time complexity of adding a node at the end will be big O1, but the time complexity of removing the last node will be big O(n) because it requires traversal. Let's understand overflow versus underflow. Stack overflow occurs when there is no space left to allocate the memory. In that case, malloc function will return null. Stack underflow occurs when the top is equal to null. Now let's move on to the implementation. So here is the program. Let's understand the program. So here we define a function to create a stack, that is create underscore stack. And then we'll define a function to create an empty stack. So here we define the function by the name of check underscore empty stack. Now let's create a function to add a node. So define push bracket stack comma item. And then we'll add print pushed item to make it easier to understand that which item is pushed. Next we'll define the function pop to delete a node, and hence define pop bracket stack. And if check empty stack, then return stack is empty. To check if the stack of the node is empty, then what will it delete? So hence it is important to know that if the stack's node is full or empty, because then only it can delete it. So then, or else it will return stack.pop, it will just delete it. Now let's add the items, that is push stack string 1. One string is pushed, then second string is pushed, then third, and then fourth is popped. So next is the print popped item plus pop stack, print stack after popping an element, string stack. So let's run this program. So here we can see the pushed item was 1, then the pushed item was 2, then the pushed item was 3, and the pushed item was 4. Hence the stack would have become 1, 2, 3, 4. But the popped item is 4, so hence the 4 is removed, and then stack after popping an element becomes 1, 2, and 3. And that's how linked list works.
I'm Manjari Gupta and I'll be talking about implementation of stack using nested lists. So stacks are last in first out data structure where the last element added is the first one removed. A nested list is a list where elements can be other lists. Combining these two concepts, a stack can contain nested lists, allowing for the handling of hierarchical or multi-level data. So why do we need nested lists? We use nested lists in stacks to efficiently represent and handle hierarchical, multi-level, or recursive structures. By allowing each element in the stack to be a list, which can contain further lists, nested lists enable the stack to manage complex relationships between elements, such as parent-child structure. Let us look at a Python code example to understand this better. Here we evaluate nested arithmetic expression using stack. So this is our expression, and whenever we find a parenthesis, we validate the sub-expression there. And when we run this code, we get a result. So nested lists in stacks allow us to handle multi-level data recursive structures efficiently, making them valuable in applications like parsing, tree traversal, and even expression evaluation like we saw. So now, what are the real-life use cases of this? Firstly, parsing nested data structures. Like in JSON or XML parsing, the structure can have nested elements. Stacks with nested lists can help track where you are in the structure, ensuring that parent-child relationships are preserved. Also in tree traversal, when traversing a tree structure, for example a company's organizational chart, stacks can manage the depth-first search, where you explore one branch fully before moving on to the next. Also, we can use it in expression evaluation like we saw in the previous exam. Let us look at another Python code example of depth first search with nested lists. So first we have defined a tree-like structure using nested lists here, and we start at the root of the tree and we pop the top element. If it's a list, it pushes its children. And then we process the node, and when we run this, we get the whole structure. So the tree is represented using nested lists here, and the stack is used to traverse the tree in depth first order, printing each node as it is processed. This approach efficiently handles hierarchical structures in real-world applications like web development and tree-based algorithms like depth first search, like we saw.
Let's see the applications of stacks in infix to postfix. So what is infix? Infix just means that the operators is between the operands. For example, 3 plus 4 into 5 plus, and the multiplication symbol is between the operands. So this is for us humans to understand this language. So there's a need for parentheses or operators, precedence, or rules to clarify the order. What is postfix? Postfix is for the computers to understand the language, just as infix is for humans to understand. Postfix is for the computers to understand. There is no particular order because the order is always clear. So there's no parentheses needed, and in this, for example, 3, 4, 5 multiplication and plus, the operators is placed after the operands. So why is there a need for, what is the role of the stacks in the infix to postfix conversion? That is humans to computer language conversion. So what is a stack? A stack is a data structure with the last item added is the first one to move. The LIFO method, the last in first out. So how do stacks help in this conversion from infix to postfix? Stacks temporarily holds the operators. They also ensure the operators are applied in the correct precedence order. They also manage parentheses and expressions. You can see the exponential has the highest value, b, followed by the multiplication division, that is a 2, that is the value of 2, plus and minus, that is the lowest value of 1. So let's see what is the infix to postfix conversion process. First, read the infix expression from left to right. We have to analyze each character, operand, operator, or the parenthesis, operands, number. We have to add them directly to the postfix output. If, for example, if A is encountered, we have to add that to the output. Let's see how do we handle operators. We have to check the stack for higher or equal precedences of operators. We saw exponential as the highest, followed by multiplication, followed by addition. We have to pop and add them to the output before pushing the current operator. For example, if plus is encountered and the stack has multiplication, we have to pop the multiplication to the output. Opening parenthesis. We have to push that opening parenthesis into the stack. For example, if A plus B parenthesis B into C, we have to push that open bracket into the stack. Closing parenthesis. We have to pop the operators to the output until the open parenthesis is found. Then we have to discard the open parenthesis. Example, if in the example B into C closing parenthesis, if closing parenthesis is encountered, we have to pop all the operators until the opening parenthesis. That is the multiplication symbol we have to pop. End of the expansion, we have to pop all the remaining operators from the stack to the output. If plus or minus remains in the stack, pop them into the output. Let's see the conversion process. A simple expression such as the A plus B into parenthesis C plus D. There's a stack given, there's iteration count which is initialized to 0. There's a prefix notation that is the expression itself, and there's the postfix notation. So let's see, we have to read the letter A and we have to directly write that down into the output. That is the postfix notation. We have to read the operator plus and we have to add that into the stack. We have to push that into the stack. Next we encounter B, we have to straight away write that down to the output. Next we encounter the multiplication symbol, we have to push that into the stack. We now encounter the open parenthesis, we have to push that open parenthesis to the stack. Now if we encounter the letter C, we have to write that down directly into the output. Now we encounter a plus symbol, we have to push that plus symbol to the stack. Now we encounter D. D is straight away written to the output. Now we encountered a closing bracket. When we encountered a closing bracket, we have to pop all the operators till the opening bracket. That is the multiplication symbol. Sorry, the plus symbol. See, with a little animation, we can see the plus symbol go straight away to the output. Now input is empty. We have to pop all the items until the stack is empty. We can see with a little animation that multiplication symbol goes directly to the output on the stack. Next away, we can also see the plus symbol. If to pop all the operators, so the plus symbol moves to the output. So this is the final output. A, B, C, D plus multiplication plus is the final postfix notation of A plus B into parenthesis C plus D. So we saw how to convert infix to postfix. That is the application. We saw how do we use stacks in the conversion of infix to postfix. Thank you.
Okay, so let's take a moment to discuss should we use stacks. On one hand, stacks offer several advantages. They are simple and easy to implement, and they allow for efficient memory management. Stacks are especially useful when it comes to recursion, as they follow a last in first out method. This makes them great for managing tasks like function calls, where the most recent call needs to be addressed first. However, they also come with certain limitations. One such drawback is its limited access. You can only manipulate the top item in the stack at any given time. Additionally, stacks also have a fixed capacity, meaning they cannot grow beyond a certain point, which can lead to overflow. Other issues like underflow can also happen when you try to remove an item from an empty stack. Memory fragmentation can also be a challenge when you're using stacks. So these disadvantages make it essential to weigh the factors depending on what your specific application is. Now let us look at how stacks apply to real life. Imagine a stack of books on a table. You can only add a book to the top of the stack. When you remove a book, you have to take one on the top. The book placed first will be the last one you remove. This simple example explains the core principle of stack, that is last in, first out. A more practical example is undo and redo function. When you type in an editor, each character is pushed onto a stack as you type. When you press undo, the last character is popped off the stack, and redo simply pushes it back into the stack again. Another great example of this would be web browsing. Every time you navigate through pages, the browser keeps track of them in a stack-like manner. Hitting the back button removes the current page from the top of the stack and takes you back to the previous one. So while stacks come with benefits like efficiency and simplicity, their limitations like fixed capacity and memory issues must be carefully considered depending on your needs. They are undeniably useful but must be used in the right context.